In section 4.3, you will learn about Riemann sums and definite integrals. Let's look at a definition here for a Riemann sum. First up, we have to let f be defined on the closed interval a to b divided into n subintervals. The x values of the subintervals, with the left endpoint being a, the right endpoint being b, then we call a x0, and then the next one is x1, x2, x3, and so on, xn minus 1 to xn, which is the right endpoint b. Now, what's different with a Riemann sum than an upper sum and a lower sum is that the subintervals can be different widths. So now each subinterval has its own designation, delta x sub I, which is the right endpoint of the interval minus the left endpoint of the interval. So if you look at this picture, xi is the right endpoint of interval I, x sub I minus 1 is the left endpoint of interval I, and delta x sub I is the width between those 2 points. Next, c sub I is any x value on the ith interval. So it doesn't have to be the left endpoint or the right endpoint. All that has to be true is that c sub I is somewhere between x sub I minus 1, which remember is the left endpoint of the ith interval, and x sub I, which is the right endpoint of the ith interval. Then the Riemann sum is equal to the summation I equals 1 to n of f of c sub I times delta x sub I. Every interval can have its own width. So you can see that this product right here just is the base of our rectangle, which is delta x sub I, times the height of our rectangle, which is f of c sub I. So this is just the area of rectangles. And of course, what we're doing here is adding those up. So it's the sum of those areas of the rectangles. So let's explore an example and see how this works. In this example, we have to find the Riemann sum for f of x equals 3x plus 2 on the interval 0 to 6 with n equals 4. So this is a graph of f of x here. We know it's linear. Now in this problem, we are given all the x values that define the subintervals. So x0 is 0, x1 is 1, x2 is equal to 3, x3 is equal to 4.5, and x4 is equal to 6. Remember that x0 is always the left point of the interval, and that was 0 because our interval went 0 to 6. And xn, which in our case is 4, so x4 is equal to 6, which is the right endpoint of the overall interval. We are also given all the x values to use in each subinterval. So in interval 1, we're told that c sub 1 is 0.6. So that means we will find the height of our rectangle by finding f of 0.6. So in region 1, this will be our rectangle. Now remember, a Riemann sum, I've abbreviated with RS here, A Riemann sum then is going to be the summation I equals 1 to 4 of f of c sub I delta x sub I. This is just the area of each of the rectangles. So our Riemann sum, we know we will need a rectangle from each area. And in area number 1, the rectangle that we will do will be f of 0.6, that's the height, times the base, which is delta x1. So we'll do f of 0.6 times delta x1. Then we have to add to that the area of region 2. And in region 2, we are being told to use an x value of 2. Then the height of our rectangle in region 2 is going to be f of 2. So this is the rectangle we are using for that region. So we will do f of 2 times the width, delta x, of region 2. So delta x2. Then in region 3, we are told to use an x value of 4. Then the height of the rectangle in region 3 will be f of 4. And then this will be our rectangle that we use. So we've got plus f of 4 times its width, which would be delta x of region 3. In region 4, we are told to use an x value of 5. So then to find the height of our rectangle, we will do f of 5. So then the area would be f of 5, which is the height, times the base, which would be delta x for region 4. So now let's start plugging in those values we get for the Riemann sum. We know that f of 0.6, if we plug that into this function, 3 times 0.6 would be 1.8. 1.8 plus 2 is 3.8. And delta x1 is just the width of that interval, so 1 minus 0 is 1. In region 2, we have to do f of 2 for the height, so f of 2 would be 8. And then we have to take that times the width of region 2, which would be 3 minus 1, which is 2. In region 3, we have to do f of 4 for the height. So f of 4 is going to be 14. And we have to take that times the width of interval 3. So we're doing 4.5 minus 3, which is 1.5, plus in region 4, let's mark that. This was region 4 right here. In region 4, we have to do f of 5 to get the height of our rectangle, and f of 5 is going to be 17. And then we have to take that times the width of region 4, which is 6 minus 4.5, which is 1.5. And if we do this calculation, we find out that the Riemann sum is equal to 66.3. So the Riemann sum is another approximation for the area under the curve, and you can see in each one there's some error. For example, in region 1, we're not covering this little triangular area here, but we are adding in this little extra triangular area here, which kind of offsets the area that's missing. In region 2, we're a little under here because we're not covering that area, but we're a little over on this side because we are covering that. So this rectangle is estimating the area that would be under the curve. Same for region 3, too little here, too much there, can offset each other, and same for region 4. So the Riemann sum is another way that we can estimate the area under a curve using rectangles. So this brings us to the concept of definite integrals. Let's use this diagram to help us understand. We have y equals f of x is this curve, and then with a Riemann sum we can have subintervals that have different widths. Now there's something called the norm of the partition, and it's denoted with this, looks like double absolute value symbols with a capital delta inside there. And the norm of the partition is just the largest subinterval in your Riemann sum here. So in this diagram, it looks like this interval is the largest subinterval. So this one would be the norm of the partition, this width. And then what happens is, as we get more and more subintervals, n gets bigger and bigger and bigger, then we know that that would mean the largest subinterval is going to get smaller and smaller and smaller because we have more and more subintervals. So if the norm of the partition goes to a width of 0, then that means that all the delta x sub I would also have to have that their widths are going to 0. Because if the biggest one is getting tiny, then the ones that are smaller than the biggest one would also have to get tiny. Now we have to ask, what must happen to n to make the norm of the partition, the largest subinterval, go to 0? Well, to make this largest interval go to 0, that means we would have to drive n to infinity, and then of course that will make all the delta x sub I go to 0. So now that brings us up to the definition of definite integrals. The definite integral of f from a to b is denoted with this set of symbols. So the way you read this is the integral from a to b of f of x dx. That is defined to be the limit as the norm of the partition goes to 0 of the summation I equals 1 to n of f of c sub I delta x sub I. So let's think about what that means. A definite integral of a function is defined to be the summation of all the areas of all the rectangles used to approximate the area under that curve, where we drive the width of the largest subinterval towards 0. Now remember, we said to make that largest subinterval width go to 0, what we have to do is drive n to infinity. So we can say instead that the integral from a to b of f of x dx could be evaluated doing the limit as n goes to infinity of the summation I equals 1 to n of f of c sub I delta x. Now notice this is our delta x that we used with the upper and lower sums. It's not delta x sub I. As n goes to infinity, the left endpoint of the interval and the right endpoint of the interval all go crashing together, so essentially they become the same point. So we can use the simplest form for c sub I, being a plus I delta x, and let all the delta x sub I equal delta x, which is b minus a over n. So we don't have to do individual widths, because if we are driving the width of all of the intervals towards 0, then we can say they're all going to have the same width, which is approaching 0. Computing this limit is typically easier than trying to compute this limit. So that's the motivation for wanting to do it. A definite integral then is defined to be this infinite limit of a summation. Now it's important to note that definite integrals yield a numerical result and may be positive, negative, or 0. So in your notes here, I put a summary for you for why the second form of the definition is equivalent to the first. So just to briefly summarize what we talked about. As n goes to infinity, the width of each interval, delta x sub I, goes to 0. So the endpoints of each subinterval and all points in between will converge together. That means we can use the simplest form for c sub I, which is the right endpoints, c sub I equals a plus I delta x, and we can set all the intervals to have the same width and make each delta x sub I just a delta x, which is b minus a over n. Because remember, if all the widths of all the intervals are going to 0, they're essentially the same thing. Then to evaluate a definite integral, we can use the easier to evaluate form of the limit as n goes to infinity, rather than the more complicated limit, which is as the norm of the partition goes to 0. So then the definition becomes the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the summation I equals 1 to n of f of c sub I delta x. And when we refer to the definition of definite integral, this is what we mean. When you are asked to find the definite integral from a to b of f of x dx, it means that you will be doing this infinite limit of a sum. In this example, we have to evaluate the definite integral from 4 to 7 of x squared dx. Now, by definition, this means we have to evaluate the limit as n goes to infinity of the summation I equals 1 to n of f of c sub I delta x. Now the interval that we are on is always the lower limit of the integration to the upper limit of the integration. So that means we are going from 4 to 7. And f of x is always the integrand. So f of x is equal to x squared. Now, like we did with definition of area, I suggest that you do your setup off on the side first. Delta x is defined to be b minus a over n. So that's going to be the endpoint of our interval, b, which is 7, minus the starting point, a, which is 4, over n. So that simplifies to be 3 over n. Next, we need to find c sub I, and we know that we can use the simpler format of the right endpoint, which is a plus I delta x. So that's equal to 4 plus I times delta x, 3 over n. So we can write this as 4 plus 3i over n. Now we have to find f of c sub I. And remember, f of x is equal to x squared. It's our integrand. So we have to take 4 plus 3i over n and square that. So we know that will be 16 plus, we have to double the product. So the product would be 4 times 3i over n, which is 12i over n. And then we have to double that, 24i over n. And then we have to take the second term and square it. So plus 9i squared over n squared. Now we are ready to plug this in to this limit definition for definite integrals. So this becomes the limit as n goes to infinity, summation I equals 1 to n. We have to put in f of c sub I, which we just found, is 16 plus 24i over n plus 9i squared over n squared. And then we have to take that times delta x, which is 3 over n. And you always want to double check that you have all of the elements here. F of c sub I is this whole expression here, and delta x is 3 over n. One of the most common mistakes that students make is they leave off the delta x. Now this becomes the limit as n goes to infinity, summation I equals 1 to n. We can distribute this 3 over n to all three pieces of this f of c sub I expression. So 3 over n times 16 gives us 48 over n. Bring down the plus sign. 3 over n times 24i over n gives us 72 over n squared times I, or you can write it as 72i over n squared. Then we bring down the next plus sign, and we distribute 3 over n times n I squared over n squared, and we get 27 over n cubed times I squared. Now we are ready to apply our summation formulas. we get limit as n goes to infinity. Now for this first one, remember that the variable of the summation is I, so it's going to treat 48 over n as a constant, and the rule there is you take your constant times n. So 48 over n times n. Bring down the plus sign, and here we're going to be summing over the I. Treat this like a constant that you pull out front, 72 over n squared, and then we have to apply the rule for summing over I, which of course is n times n plus 1 over 2. Then we bring down the next plus sign. We can treat 27 over n cubed like it were a constant because it doesn't have the variable I in it. And then that means we will be summing over I squared and using that rule, which we know is n times n plus 1 times 2n plus 1 over 6. And we close the bracket. Let's simplify. We have limit n goes to infinity. The n's cancel in this first term, and we have 48. Bring down the plus sign. 2 goes into 72, 36 times. The n up here cancels one of the n's down here, so then we have n plus 1 over n left over. Bring down this plus sign. 27 and 6 have a common factor of 3, so if I take 27 divided by 3, I get 9. 6 divided by 3, I get 2. This n will cancel one of the n's down here, and we are left with an n squared in the denominator. And then in the numerator, we need to multiply out this binomial, which is 2n squared plus 3n plus 1. Close the big bracket. Now this is going to equal the limit as n goes to infinity. We have 48 plus 36 times. We can rewrite this rational expression as n over n, which is 1, plus 1 over n. Bring down the plus and the 9 over 2, and we can rewrite this rational expression in 3 pieces. 2n squared over n squared becomes 2. Then we have 3n over n squared becomes 3 over n, and then we have plus 1 over n squared. Close the parentheses, close the bracket. Now we can go ahead and evaluate the limit. As n goes to infinity, that means 1 over n is going to go to 0, 3 over n is going to go to 0, and 1 over n squared is going to go to 0. So this becomes 48 plus 36 times 1 plus 9 halves times 2. So we have 48 plus 36 plus 9 is equal to 93. So what we just discovered is that the integral from 4 to 7 of x squared dx is equal to 93. So just a reminder about our note from the definition of definite integrals. Definite integrals yield a numerical result and may be positive, negative, or zero. In this case, this definite integral from 4 to 7 of x squared dx was equal to 93 and happens to be a positive value. Next up, we look at the area under a curve. If f of x is non-negative, and remember, non-negative means that f of x is greater than or equal to 0, because remember, a function can be in three states: positive, negative, or 0. So non-negative means 0 or positive. So if f is non-negative, then the area bounded by f of x, the x-axis, the vertical line x equals a, and the vertical line x equals b is known as the area under f of x and is given by the definite integral from a to b of f of x dx, which we now know is defined to be the limit as n goes to infinity of the summation I equals 1 to n of f of c sub I delta x, where c sub I is a plus I delta x and delta x is b minus a over n. Now in this diagram, the area bounded by all of these is this area right here. So when we talk about the area under f of x, this is what we mean. It's under f of x, but above the x-axis, and then bounded by the left endpoint of the interval and the right endpoint of the interval. Now in this example, we have to find the area under f of x equals negative x squared minus 2x from negative 2 to 0. We recognize that this is a parabola that opens downward. We can factor it, pull out a negative x, and then we would have x plus 2. So that makes it pretty quick to graph. We know the roots are at 0 and at negative 2, which means the vertex would be halfway between there at negative 1, whatever that highest point is. So then the area that we are finding here is this area. And we know from this definition, if f is non-negative, and we look on the interval we are at, our interval is negative 2 to 0, and f of x is greater than or equal to 0 on that entire interval. So since f of x is greater than or equal to 0 on the interval negative 2 to 0, then the area is given by the definite integral, and in our case it will be from negative 2 to 0 of f of x dx, so negative x squared minus 2x dx. And so now we know that to evaluate this integral, we need to do an infinite limit of a sum after we set up delta x c sub I and f of c sub I. Now we're ready to find the area. We know that the area is a definite integral, which is defined to be the limit as n goes to infinity of the summation I equals 1 to n of f of c sub I delta x. So let's do our setup. We know delta x is always b minus a over n. So in this case, that's going to be the end of our interval, which is 0. That's the upper bound of the limit, minus the beginning of our interval, which is -2, and put that over n. So that equals 2 over n. Then we have to do c sub I, which we know is a plus I delta x. So that's going to be -2 plus I times 2 over n. So we can write that as -2 plus 2I over n. Then we have to do f of c sub I. So we have to take our c sub I expression and put it into f of x is equal to -x squared minus 2x. So that means we will have negative of our input squared, so -2 plus 2I over n squared, and then we have to subtract 2 times our input, which is -2 plus 2I over n. Now we have to simplify. Let's bring that negative sign down, and then squaring this binomial, we get 4, and then minus double the product, so 8I over n. The last term squared would be plus 4I squared over n squared. Now we have to distribute this -2 into this binomial. So we would get plus 4 and minus 4I over n. Now here you can see we will have a -4 from here and this plus 4 here, and those are going to cancel out. We will have a positive 8I over n minus 4I over n, so that's going to be positive 4I over n. And then this negative sign will distribute to the third term here, minus 4I squared over n squared. So now we have delta x, and then we've got c sub I, and now f of c sub I. Now we know all of these pieces, so this becomes the limit as n goes to infinity of the summation I equals 1 to n. F of c sub I is this expression down here, 4I over n minus 4I squared over n squared. Then we have to take that times delta x, which is 2 over n. So this will equal the limit as n goes to infinity, summation I equals 1 to n, and we have to distribute the 2 over n in, and we get 8 over n squared times I minus, we get 8 over n cubed times I squared. Now we can go ahead and apply the summation formulas. So we have limit as n goes to infinity. Now remember that the variable of the summation is I, so we're going to pull this 8 over n squared out like it were a constant, and then we will do the summation over I, which tells us to do n times n plus 1 over 2. Then we bring down the minus sign, and for this term, once again, we can treat the 8 over n cubed as though it were a constant, because in the i's of the summation, the variable is only I. Then we are going to do our summation formula on I squared, and we know that that's going to be n times n plus 1 times 2n plus 1 divided by 6. Close the big bracket. We continue to simplify. This equals the limit as n goes to infinity. 8 over 2 simplifies to be 4. And then this n up here cancels one of the n's down there. So we have n in the denominator and n plus 1 left in the numerator. Bring down the minus sign. 8 over 6 reduces to 4/3. Then this n in the numerator cancels one of these n's in the denominator. So we're left with n squared in the denominator. And then we will FOIL out this binomial to get 2n squared plus 3n plus 1. Make our parentheses here and then close the big bracket. Continuing to simplify, we get limit as n goes to infinity. We have 4 times the quantity, n over n becomes 1 plus 1 over n minus 4/3, and we have 2n squared over n squared becomes 2 plus 3n over n squared becomes 3 over n plus 1 over n squared. Now we can let n go to infinity, which means this will go to 0, this will go to 0, and so will 1 over n squared. Also goes to 0. So this first term just simplifies to 4 times 1 minus the second term just becomes 4/3 times 2. Continuing to simplify, we have a common denominator of 3. So we have 12/3 minus 8/3 is equal to 4/3. So the area under f of x equals negative x squared minus 2x from negative 2 to 0 is equal to 4/3.